Welcome to this year's Milliman Lectures. I'm Terence, Chair of the Math Department. We're delighted to have Professor Terry Powell as our Milliman Lecturer this year. I'm sure many of you have heard about at least some of his many accomplishments and recognitions. I'll call upon my colleague Art Smith to say a little bit more about those and to introduce him. Let me tell you a few logistical things. There will be a reception after this lecture in the Peterson Hall room of the library. That's the bridge that goes over from the top. You walk through, you'll see it. Connects to two bits of the library. And you're all welcome. Please come. And today's lecture, as you know, is the first of three. There are two more lectures, same time, same place, tomorrow and Thursday. And as many of you know, this series of lectures is supported by the department's Milliman Fund. That was started in 1983 by a gift from Grace Milliman Pollock in recognition of her brother Wendell Milliman, who was a graduate of our department and a co-founder of Milliman USA, one of the largest actuarial firms. So we're delighted to have that support. It supports many other visitors to the department besides the annual Milliman Lecture.
Well, to give a thorough account of the areas in which Terry Powell works with the lecture itself, but a fairly accurate and concise summary is that he works at the interface of harmonic analysis, combinatorics, and number theory. And this is an area in which there's a long history of fruitful interaction, including the seminal work of Hardy and Liquid. And in recent years, there's been particularly strong activity, thanks in large part to the work of today's speaker. And just to give a select list of significant results that he's obtained with his collaborators, in addition to those we'll talk about in these lectures, we have to include his work on some ability of Fourier series and geometry of vector sets, existence results for critical nonlinear partial differential equations, Lorentz conjecture for eigenvalues of Hermitian matrices, and results on the recovery of compressible signals from partial data. So this last result in particular is getting quite a lot of attention due to its implications for image processing and compression, and in fact earned him a place on Computer Science's list of 10 most influential scientists of 2006. His work has also been recognized by more traditional top honors in mathematics, including the Salem Prize, the Lochner Prize, the American Mathematical Society's Pocher Prize, and in 2006 a Fields Medal and a MacArthur Fellowship. So we're very pleased to have Professor Powell as this year's Milliman Lecture, and the title of today's talk will be Additive, Combinatorics, and Primes.
Pleasure to be here. My first time, or my second time in Seattle, my first time to speak here. The weather is a refreshing change. So in my three talks, my three talks have a common theme of arithmetic combinatorics. Of which additive combinatorics is a subset. A very new field and a very old field. It's an old field because additive combinatorics has been around for quite a while. It's not by its name. It's sort of descended from two much older fields, I guess, additive number theory. And pure number theory. Somehow, the field itself, we sort of done another behind to some extent, and we just do the addition of combinatorics directly. But it's still very close to its parent fields in number theory, and today I will talk, in fact, primarily about the applications of additive combinatorics to number theory, especially additive number theory. So what is additive combinatorics? So that's sort of a one-line description, I guess. Additive combinatorics, if you like, is sort of the study additive patterns, or additive operations, or additive anything really, additive patterns in general sets sets of integers. Or more generally nowadays, or in any other added group of addition or group. Okay, so the key word here is general. Okay, so I mean, everybody uses addition in mathematics. But additive combinatorics focuses on the properties of addition that pertain to very general classes of sets, not as opposed to sets of lots of algebraic structure where you can do all kinds of things. You can do lots of algebra. We're interested primarily in sets in which you can't use algebra. There's no algebraic structure. You have very general sets, and all you can do is combinatorics instead. Arithmetic combinatorics is the same thing, except that instead of taking additive patterns, you take additive and multiplicative patterns at the same time. Arithmetic is a primary school sense of addition and multiplication, and of course now you can do it in a ring rather than an additive group, but it's sort of the same thing. Okay, I'll talk about arithmetic combinatorics in the third lecture. First two were entirely about additive combinatorics. Okay, so I said that additive combinatorics is the study of general sets of integers. By general, I really mean those sets without much usable algebraic structure. Okay. If you have lots of algebraic structure, you shouldn't be doing combinatorics, you should be doing algebra. But if you don't have algebraic structure, then this turns out to be very helpful. So what do I mean by this? Well, let me give two model examples here. So a set with lots of algebraic structure, a set of integers with lots of algebraic structure, a good example are square numbers. Very algebraic set. You have explicit formulas for say what is the nth squared number, n squared, and so forth, like and lots of algebraic structure. Product of two squares is squared, and so forth. Okay. Okay. What is a set without much algebraic structure? Those are my favorite set of prime numbers. Okay. I mean, in principle, it's an algebraic set. It's defined in an algebraic way. But in practice, the algebraic structure is not so useful. You know, for example, I can tell you what the millionth square number is very easily. To tell you what the millionth prime number is not as easy. Yeah. I mean, there's certainly algebraic structure. It's especially multiplicative structure. The product of two primes is not a prime, very bad. The additive structure is much harder. It's not two primes, usually not a prime either. But you know, there's sort of a partial amount of algebraic structure you can use. You know, I mean, there are very useful facts. I mean, for example, the primes are all odd with one exception. So that's a useful algebraic fact to know. They're all adjacent to a model of 6. Few exceptions, and so on and so forth. You have all this sort of, you have some control, but it's not enough to settle many questions. Okay, so let me write down some results and conjectures about the squares and the primes. They look very similar, but they are proven in completely different ways. So all the results about the squares you prove using algebra, and all the results about the primes you prove using combinatorics, we can't prove them at all. So, for example, we have this classical thing of Lagrange, with the Lagrange four squares theorem. Which is that every positive integer is the sum of four squares. So, for every positive integer n, there exists a pattern of the form A, B, C, n minus A minus B minus C. There exists some pattern of this form which finds out the squares. So this is a very strange way of writing the fact that every number is on four squares. Okay. So the squares contain this type of pattern for every n. The same fact is sort of known for primes, just with the Gauss theorem. What's the equality of the Gauss theorem? Which is that for sufficiently large n are the sum of four primes. Large n, there exists A, B, C, n minus A minus B minus C in D primes. Okay. If you're odd, if you're sufficiently large, if odd, you just need to do the sum of 3 primes, but you're even, the best we know right now is the sum of 4 primes. Okay. What does sufficiently large mean? So Vinogradov proved this theorem for sufficiently large n. He didn't say what sufficiently large meant. Later we actually computed bounds and how large n has to be before we can actually say this is true. The best bound known to this, by the way, is as long as n is bigger than 10 to the 13th form. It's not every number less than 10 to the 21 or something. Some of 4 primes, right? It's a completely different map. Okay, so there's still a gap there to be resolved. Okay, so those are some results. Let's see another result. Okay, so then there's the Martin squares theorem. So what about sum 2? Well, if you have any number which is any prime is 1/4, then Fermat showed that it exists. Every prime which is 1/4 is the sum of 2 squares. Okay? It's a nice classical theorem. The first algebra class. Class. Okay, the corresponding question for primes is not known, so you can go back to lecture. For even numbers n bigger than say 4, it should be a pattern of form a n minus 8 at the prime. Every even number bigger than 4 should be the sum of 2 primes. So we don't know that. We don't know that. Even for sufficiently large n, it's not known. For good reasons, actually. Okay, so there's that. Fermat also proved another 4-square theorem. So he showed that the square numbers don't contain progressions of length 4. So there does not exist any arithmetic progression a equals b equals 2b equals 3b, and the squares of course would be 0. So there's so you can find progressions of squares of length 3, that's not hard, and 2 of course is pretty easy, but 4 you cannot do. That's certainly not higher than 4. Okay? In contrast, of course, there's a theorem of Ben and myself, which is that in contrast, the primes actually contain lots of progressions, so that in K, there exists in many, well, this is A and B, A equals B equals 2B, and so forth. You can find an arithmetic progression of any length you please, 10, 1,000, 1 million, in the primes. Of course, again, degeneracy speed is not likely 0. Okay, so we have this theorem. It's sort of an indirect theorem. We don't actually reduce the progression. We just show that they exist. The largest progression that's actually been found is of length 23. It's found by some computers earlier this year. Okay, we'll show that it's somewhere in the primes. Okay, and the last thing to complete this table is, well, it's not, I think it doesn't have a name, it's called Gauss equation. Okay, that there are infinitely many solutions. There are infinitely many pairs, A is 2A plus 1, which are both squared. The more traditional way of writing this is that you present infinitely many solutions to this equation n squared minus 2n squared equals 1. Okay, so this is an old result, and the corresponding conjecture for the primes unknown is also the mean conjecture. So we know that there's infinitely many squares, such that if we just double it, you add 1 to the square. Not right. I'll check that. Okay. But okay, the infinite many patterns of this form, but we can't prove the same thing about primes. In fact, this conjecture is very, very similar to this conjecture. You see basically the there's only one free parameter to play with. And basically, we don't know how to count things in primes when there's only one, when you only get to choose one parameter. When you get to two or more parameters, we have lots of tricks. So, I mean, I put this table up to sort of suggest that there seems to be this parallel between primes and squares, but the point I wanted to make actually is that there's a lot of differences actually. So, the first thing you notice that all those actual squares were proven 200 years ago. So, the pose equation, I mean, this fact about when you get the form, this was known to Atlantis in BC or so. It was also known in ancient Indians. And because these are also very, very classical. These are also all 20th century or unsolved. So, the primes are a lot harder than the squares. Basically, the squares, adding squares together, you have all these lovely algebraic formulas. Of course, basic ones is this one factorizes some two squares into Gaussian integers. You can factorize the say n squared minus 2m squared into integers over 2 and so on and so forth. You can do all kinds of tricks, factorization tricks. You can relate these problems to quadratic forms. You can relate them to elliptic curves, SL2Z. There's all sorts of algebra you can use. But for the primes, there's very, very little. I can't factorize it. There's no formulas. If it's some two primes, it doesn't split into something particularly useful. There's no glue back into the primes. It does anything interesting. There's no algebraic structure. So instead, well, I mean, there's some, but very, very little, especially additive. Multiplicatively, there's some, but additively, there's very little. I guess, okay, there is one important formula about the primes that is incredibly useful. So, conventional, I guess. Okay, so the primes do obey one nice arbitrary formula. This is all the primes to any power s, v minus s, you get the v minus zeta function, which is let's say for s bigger than 1. This is a very fancy way of saying unique factorization. Every number is unique to the product of primes. That's the power series expanded out like this. And so this is the one algebraic fact that we have about the primes. It is incredibly useful, provided that you understand this guy. Now, we do understand a little bit about this guy. Not sure we can say some non-trivial things about the primes. For example, if you find number theorem. This and knowing something about zeta, is you find number theorem. The number of primes less than large number n, you can't compute exactly, you can compute it approximately. Number of primes less than big number n is equal to n over log n, plus an error which goes to 0 as n goes infinity. So asymptotically, we know how many primes are less than big number. So it's a number theorem. So you can say some stuff about this using this, but of course, we don't know as much about zeta as we would like. And so we don't, this formula doesn't tell us everything. In fact, even if we did know everything about zeta that we wanted, even have to say the Riemann hypothesis and some of the generalized Riemann hypothesis, this board here wouldn't change very much. We would still not be able to solve the conjecture even for large n. We would not be able to solve sufficient amount. You don't get any proof of R here. The one thing you can do, if you assume something called the generalized Riemann hypothesis, you can show with an Evaluator scheme that this state is actually true for not just for all large n, in fact for all n, bigger than 8 or something. You can at least get rid of that gap in GRH. But basically, this formula is really a multiplicative formula. As I said, it's proven by observing that every number can factorize uniquely into primes. And it tells you a lot about multiplicative structure of the primes, but not about the additive structure. You can't prove any additive pattern. So these are all additive problems. You see that we're all looking for patterns in the primes and all in the squares, and they all involve either addition or subtraction, additive patterns. Okay, but apart from this one very important fact, the primes really don't have much usable algebraic structure. So we need tools that don't use structure, and that's where combinatorics comes in. So let me give you a very simple example of how to use combinatorics to say stuff about a set which you don't know anything, or if you know absolutely nothing, so you can't say anything. you know very little about this. You can still say surprisingly quite a bit in combinatorics. So let me give you an example. Let's define a parallelogram. Okay, so by parallelogram, I just mean four numbers on A equals B equals C equals B equals C. So four numbers. It's a one-dimensional parallelogram. And I guess to avoid degeneracy, let's make B and C non-zero. Okay? And, all right, so I think I'll give you a very simple result. Okay. Theory is so simple, but here the primes contain many parallelograms. So a typical example is 3, 7, 43, 47. Okay, it's a parallelogram. Okay, so superficially this result looks a lot like say our result if we had many progressions, parallelograms. But this is really easy. And you prove it without using very much of the primes. In fact, the only thing you need to know about primes is a lot of primes. You need this fact. Okay, so how do you prove this fact? So it's actually very easy. You pick a large number n. Okay, okay, so there's infinite many primes, but let's just take some of them. Let's just take say p sub n. Let's just take all the primes p, which are between say n and 2n. Okay, we take all the primes that have ranged from say 1 trillion to 2 trillion, so there's a lot of those. Our number theorem tells you how many of these are up. So roughly about n log n still. Times over s. Okay, so now we do the following. Look at the primes. So we have a lot of primes here. We look at differences of primes. Okay, so we take 2 primes in here. We look at the difference. Here I see two distinct primes. We take 2 distinct primes in p sub n. We look at the difference. So this is some number between n and minus n and not 0. Okay, so we can take all the primes and form the differences. Now there's lots of differences. Okay, if we have this many primes, the number of differences we have, so the number of differences counting repetition is going to be basically this squared. Okay, you have to cut out the diagonal of the p equals that's actually a very small contribution. Okay, so there's lots of differences counting repetition. On the other hand, the number of differences here, the number of possible values the difference can have is only n equals 2n. Okay? And n is big enough, n squared over log n squared, even with this little error, is bigger than 2n. So for n big enough, you have more differences than values, and hence by the Cushinol principle, classic combinatorial technique, two differences must be the same. So you have to define one pair, with another pair of difference primes. And then to rearrange this is just saying a p, q, r, and s on a parallelogram. And so what we've shown is that all the primes between n and 2n are individually on a parallelogram. In fact, you can run this argument, in fact, the argument shows that you actually can make a lot of parallelograms. You don't just use the Cushinol principle, but you use this quantitative big brother for the Cauchy-Schwarz inequality. You actually show that here you can use a lot of parallelograms. Again, it's actually quite big. N cubed over the fourth. But essentially, it's number here. Okay, so there's actually quite a lot of parallelograms in the primes. Okay, so this is a very, very simple example of how you use very simple result of additive combinatorics. This is a very special case of the generated cube number. You notice that, it's a theme about primes, but maybe we didn't even about primes at all. If you know anything about primes, there's a lot of primes. But just from that, you can say stuff. Right? You can say that any set which is sufficiently big contains, say, parallelograms. Very roughly speaking, the way that I prove this theorem here. we use a very similar fact here. So, so what we really proved there is that what we really proved was that any sufficiently dense set, any sort of dense set of integers. And then the primes happen to be dense enough that you can apply this theorem. I don't really want to talk about this theorem, but talked about it so many times already, but I'll just mention a few things about it. So the way we put this theorem is that it turns out to be a similar, so this result, as I said, is a special case of what's called the semi-cube lemma. It's the two-dimensional version of the semi-cube lemma. It turns out that every dense set was connected to many parallel pi beds, which is the same thing that they give 8 of these guys, but 4 of many cubes of any dimension, in fact. Anyway, so with this theorem, Zimmermann also put another theorem much harder, called Zimmermann's theorem. Which says that every dense set, and I won't define what dense means. Every dense set contains arbitrarily long diagonal progressions. And if you could apply this theorem directly to the primes, you could just very cheaply get the prime dependent arbitrary arithmetic progressions too, it's out here. So we couldn't quite get away with that because it turns out that the density that Zimmermann's theorem needs is a bit too dense for the primes. I can move on which type. So when Zimmermann says the set is dense, what it actually means is that the number of elements in your set which are less than n, larger than n, over n has a positive limit. If you positive assume. Density of the size. But this is actually what you need. Unfortunately, with the prime number theorem, what it shows you is that the density of primes up to n is only 1 over log n equals to 0. So we can't actually use this theorem directly. But what we're able to do is we're able to take this theorem and sort of stretch it a little bit and say, once you know that every dense set contains loss of progression, it does allow you to say that certain sparser sets also contain loss of progressions because certain sparse sets can be modeled by dense sets which have very similar properties. And as a result, we reach this dense sets into sparse sets. But I really don't want to talk about this today. Mention it. Okay. So something a bit different. Okay, so all right, so I showed you this very simple combinatorial argument that lets you do parallelograms, but what do you want to do something else? What do you want to see? So the Goldbach problem. Okay, so this even Goldbach conjecture, that's really hard. Let me talk about the odd Goldbach conjecture, which is a bit easier. The odd Goldbach conjecture is the statement that every odd number bigger than 7. Times. And on number n, you can write n as a equals to c. Okay, so we can't do this problem yet. As I said, Vinogradov was able to show this as long as it's even big enough in terms of 30, 40 years ago. If you assume the general Riemann hypothesis this was true, it's a theorem, but it's unconditional, we don't know it yet. Okay, but to explain why Vinogradov was able to even get somewhere on this problem and find nobody even in the Goldbach problem, the even Goldbach problem, we'll talk about how you would prove such a thing by combinatorics. You have some number n, and you have some set p that you don't understand, and you want to write n as a sum of where n is the sum of three numbers from P. Okay, so let's work with a toy problem. So the primes are hard to understand. A couple of ones are kind of sparse, which does some problems. So really, the toy problem. Instead of working in images, let's work in a finite cyclic group. Okay, so we take a large cyclic group. We pick some element x in here, and we take three sets A, B, C. And we ask the question, okay, when an x is written as a sum A plus B plus C, where A is an A, B can be C. Okay, so this is a sort of a robot type problem. So you have so here we have three guys from the same set. I generalize a little bit, three guys from different sets. When can you write a given element x as the sum of three guys from arbitrary sets? Now, of course, if I don't know what A, B, and C are, you can't answer this question. Okay, you need to assume something about A, B, and C. So for example, A, B, C are empty or something. You can't do anything. So supposing that A, B, C is really large. Let's say, for example, that they all can see at least say 10%. So A, B, C occupy 10% of the C each. Okay. Now, can I be large? So previously, I just this is a large set of parallelograms. Maybe now, once it's large enough, then I can write any x I wish as the sum of my three sets. Now, unfortunately, these are large, but not large enough. That be true. This is not just knowing this is a large can't solve this problem for me, because as common examples, I could take A to be just the first n over 10 integers, let's say n over 10. And I could take B and C to be the same thing. And then you can see that you can't actually write every number in this group as the sum of three guys, as the sum of A's and B's and C. You can only write 30% of them. Everything less than 3 over n, 3 over 10n minus bigger. Everything 3 and 3 over 10. You can write, but nothing else. So from just this assumption alone, you can only represent about, say, 30% of the numbers. C. Another example, if n is multiple 10, then A, B, and C be multiples of 10. This is a subgroup of your set, and subgroups are also closed in addition. And so if you're not multiple of 10, you can't be written as a sum of the rest of it. Okay? So there are examples, there are these various examples that show that you can't always solve this problem. But you notice that these examples are very algebraic. Okay, this is a subgroup. Okay, algebraic from that. Okay, this is a nice one conversion. And it turns out that in some sense, these algebraic examples are sort of the only obstruction, the only thing that are blocking you from solving this problem. It turns out that if even just one of your sets doesn't look like one of these examples, then you can solve this problem no matter what, as long as it's what you do. And so let's do it. Let's just do it if I can say it. You see, I said at the beginning that combinatorics, additive combinatorics deals with things that have no structure, and you may think, well, that makes your life harder. You have less tools to do. In some ways, once you have no structure, things actually get easier. And you can actually prove things that you couldn't prove in your structure. So, I can't tell you that every number is the sum of three numbers here if your sets are very structured. If your sets are the opposite of structured, anti-structured, if it's pseudo-random, then you can actually start to work on something. And you don't need algebra at all. You just say, well, this can come first. Okay, so, so how should I proceed? So, let's try, what I'm going to do is I'm going to argue like I'll assume that I can't solve this problem. There's an x I can't do something C, and from that I'll conclude that there's something funny going on with A, B, and C. Then taking these actually will be something like this. Okay, so start. So suppose that x, such that x is never the sum of three elements A, B, and C, for any A, and A, B, and B, C, and C. Suppose you cannot solve this for a but nevertheless A, B, C are large. Okay, so you can actually convert this lack of solution into something more constructive. Okay, so what does this mean? So this means that if you look at solutions X, I'll move KB on the other side. What this says is that given, so C can be anything in big C. So another way of saying this is that X minus A minus B, so any A in A, and B in B, this expression here, X minus A minus B, does not lie in C. Now, that's actually quite a strong statement. If you think about it. Use the cyclic of Z and Z. This is really discrete. Okay, I've got this big, I've got like n over 10 numbers here. Okay, but n over 10 numbers here B, and I've got some set C, which is sitting on about a tenth of the integers here, or a tenth of the numbers here. But so there are n squared over 100 or so possible pairs A and B I can choose here. But no matter which pair I choose, X minus A minus B, it's always miraculous numbers to miss this set and land in the other 90% of space. And that is actually a very unusual event. If you take sort of n squared over 100 numbers at random, just from the law of large numbers or something, we should expect it to sort of evenly distribute throughout these n numbers here. But somehow there are these 10% of the group which is always being avoided. And you can leverage that. So you know that X minus A minus B is concentrated, what is contained in only 90% of this space. Now we can use a fictional type trick again. So before we were able to cram a lot of numbers into a small space, we had lots of collisions because they're equal. Here we actually have a lot of pairs, like n squared or so pairs, sitting inside a fairly cramped set. And so you actually get a lot of collisions. Now, the precise statement uses the kind of Schwarz inequality, but let me just say it informally. Just from the fact alone, you can conclude that there's a lot of collisions. X minus A minus B is going to equal X minus A prime minus B prime quite a bit, because you cram a lot of numbers of this form into a small space. So this happens for this for A in A, and A prime in A, in B prime in B. Happens more often than you expect. Okay, there's a precise balance, I don't want to say it. It happens about 10% more often than you expect. And more than one expects, more than we first expect. There's some elevated chance of collision. There's a precise lower bound you can make on how many pairs you have here. Okay, so how do you do this? Okay, so one nice thing about this statement is that C is gone. We have 3 arbitrary sets A, B, and C, and now C is gone. We now only have 2 arbitrary sets. Okay, so now what we do, we keep going. I take this and I manipulate it. We have X, that's nice too. And so what this is saying, what it's saying is that there are many differences of A which hit differences of B more often than you would expect by random chance. And what that really means is that the differences of A and the differences of B must both be concentrating in sort of the same region of space. And that's the only way that you can make them collide. And again, so in particular, A minus A prime, these differences are being compressed into a small space, so again, they must collide with themselves. And you can, again, make that precise, again, using the Schwarz inequality. Actually, Schwarz is that two vectors collide with each other, and they also collide with themselves. But if this thing hits this thing a lot, then you can conclude, I mean, it's again like the original principle, it's just a quantitative illusion, that some difference of A must collide with other difference of A quite a lot. So you'll be able to find solutions to this equation more often than you expect. So there are more patterns of this form than you expect random chance. So what is the solution to this thing here? That's nothing more than a parallelogram. Okay? So what you can conclude here is that you start with the statement that you cannot solve the Goldbach problem here. And what it implies for you is that the set, it tells you, it doesn't matter what B and C are. All you need about B and C are their debts. But it tells you something about A. So A has more more parallelograms, and you expect by random chance, then random chance predicts. Okay, so you can detect that there's a problem with the drawback problem without ever looking into C. Arbitrary sets is dense. So what? Well, take the contraposit. So therefore, if A has about as many parallelograms as random chance predicts, then you can something like that. Next. So this is great news. It gives you a strategy. That's a little bit problem, but you want to write a number sum of 3 primes. Start counting how many parallelograms of one. If they have sort of the number that they would have if the primes were randomly distributed. Now, I won't say what that means. Then you could use that. You could make this argument rigorous and in fact conclude that every number, at least every large number, is sum of 3 primes. Now, it turns out that with primes you can't quite do this because the primes are not actually distributed randomly. As I said, there is some structure to the primes, such as primes are almost all odd. And okay, because of that, by the way, it's much harder to write even numbers than 3 primes as opposed to sum of 3 primes. So there is this problem here that's not being picked up here yet. But you can and well, so basically what's happening is that because the primes are all odd, they actually get about twice as many parallelograms just from that fact alone. They get about twice as many parallelograms as they would have random chance. Because the basic fact is 3 points of parallelogram are odd numbers, and 4 points are odd as well. Okay, so because so if the set was totally random in ratio, but not completely random, there's still a little bit of residual structure that you have to deal with. But that turns out to be fairly easy to deal with. Due to the fact that primes are all odd, what you can use is write every prime as a form, 2q plus 1. Okay? And so the prime is odd, you can write it from 2q plus 1. And q now could be either even or odd. And in fact, there's a theorem of Dirichlet's is that this number is just like even, so it's odd. And so instead of working with the primes, you work with primes minus 1 divided by 2. And then these guys have no further bias between even or odd, and this form disappears. There's still the problem that they are biased 1 to 3, but then you can just simply with that, and so on and so forth. And so it turns out that this structure is not really a problem, basically because it's so simple that you can identify. But anyway, going back to this model problem, so if you can count parallelograms, you can do multiple things. And in some very vague sense, this field is also proven by a similar strategy, except that once you having progression, it turns out that you can't count parallelograms, you count some bigger hypex or something. But roughly speaking, you have the same sort of strategy. Okay, but how do you count parallelograms? So I figured the simple argument is this lower bound, which is the random chance lower bound, but we want to actually get a more precise count. Not just a lower bound as to how many parallelograms are. Exactly how many parallelograms does this set have? So this is where the subject gets complicated. I mean, up to now, I basically the most difficult thing I showed you is the Cauchy-Schwarz inequality. And the prime number theorem, but you just take the black box. Okay, things get a little bit more complicated now. So, of course, with progression, some of these things are still so. But, okay, so it turns out this lovely formula that if the beta subset of cyclic group, then no parallelograms in A, so math algebraic formula is actually equal to n group times the following sum. So we'll see the second group. exclusive union of n. Okay, so this is weird formula. You take this set, you take this indicator function, which is 1 on A and 0 outside of A, you take its Fourier transform. Initially, this sounds random to you. Okay, just you're so desperate, you pull out some book you like, and that can Fourier transform. Okay, then you take this Fourier transform. Then you have this very pretty formula that expresses the number of parallelograms in A as the sum of these 4 functions. Why is this formula true? Well, if you just plug it in and it's true. Let me maybe do one thing that's true. So what's parallelogram? Parallelogram is from A equals B to C equals C. That's parallelogram. What do parallelograms have to do with this Fourier phase here? Well, this is algebraic identities. I think obvious. It guides everything. You take four Fourier phases together, indexed by 4 points on the parallelogram, then magically all these guys cancel. Okay. Now that, you've seen that, okay, this identity, once you have it, and if these 4 numbers did not form parallelogram, then you would not take them. Once you have that identity, actually this thing just follows by mathematical algebra. Why is this true? This is really just a statement that you take the function instance x to, I think, x, c, or n, and you essentially twice get 0. Okay. That's, I mean, well, it's not really differentiation, it's discrete differentiation with divided differences. But linear functions have fancy derivatives. And so that's why when you calculate them on parallelograms, you get 0. And that's why linear phases, which is what Fourier analysis is all about, is parallelograms. Okay. Now, once you have this formula, it becomes very useful. Now, suppose A has some density. Suppose A has the density delta, so in my example, it's delta 110. So the combinatorial argument I said before, if your set has density delta, you can count the number of parallelograms in A. And it turns out that this is something actually Schwartz problem. The number of parallelograms in the set A is bigger than has a lower bound. This is the bound that you get by random chance. Where does this bound come from? You can think of it this way. Suppose you think A is a random set, so set density delta. So every number has got a probability delta of lying in the set. Then every parallelogram, the 4 numbers, the chance that they all lie in A is truly random, can be delta 4. But how many parallelograms are there? Well, there's 3 parameters, A, B, and C, from 1 to n. So this is how many random predicts. And if there's a lower bound, if you're not random, you get more parallelograms than usual. If you plug this into this formula, the density gives you the 0 Fourier coefficient. So 0 delta. So what this is n cubed, this is delta to the 4, plus everything else. So this Fourier formula actually, so one of the first things it shows is that it really explicitly shows this combinatorial, it gives you a different truth this combinatorial fact. That the number of parallelograms is equal to delta 4 n cubed plus some other stuff. But what makes this formula so great is that not only does it reprove this bound, it tells you when this bound is close to being sharp. Okay, so as I said before, like if you know that your set has close to this number of parallelograms, you can start doing things like certain control packaging. So, as a corollary of this, what this tells you is that A has close to the random number parallelograms if and only if everybody here is small. Okay, if and only if every class is small. Okay, what does that mean? If you come back here, that means that A does not correlate. Linear phases. Other than constant phase 1, which has to correlate. But all the non-constant phases can't correlate. So this is consistent with our counterexamples, which I unfortunately raised. You remember for the go-back problem, I gave you, so that you have a set like this, then you can't always solve the go-back problem. This set can be a set like this. No swing trouble. But these sets, these are precisely the type of sets that do correlate with phases like this. See, this guy here correlates with this trait, equal to 2 pi I x times 1. See, this on this set, this phase, this phase eventually goes around in a circle very, very slowly. But for the first 10% of his life, it's stuck on a small arc in a circle. And so there's a lot of correlation between this set here and this phase here. This set here is even more strongly correlated. This guy correlates with this phase. X times 10 over 10. Okay? This phase, in fact, this phase goes around 1/10 of a revolution every time, but at a multiple of 10, it always hits 1 again and again and again. So this set here has an extremely strong correlation with space. So now we understand things a lot better. The reason why we couldn't solve the go-back problem for these sort of sets is because they were secretly trying following some linear phase. And conversely, if your set's not correlating with a linear phase, then you can solve these sort of problems. Okay, and then so this is basically, well, not in this language, what about did. So once you see this, this is a classical discipline by the Additive circle method. Once you see this, you now know what you need to do in order to understand things like the go-back primes. You want to study the primes, and what you some system of 3 primes, you need to see whether the primes correlate with exponential phases. And so very quickly you start staring at things like this. So all primes less than n equal 2 pi I p times some phase. Exponential sums, and you have to start estimating these. Now, at this point, combinatorics doesn't help you anymore. You have to actually start using loop and look at the theory. If you look at this, no functions come in and that's all it is. But this is something which number theorists are sort of usually comfortable doing. This is a simple problem with 1 prime. So what combinatorics learns you start with combinatorics, say 3 primes, and how they call it. And after all this, you now have just to deal with something with 1 prime. And number theorists actually do understand 1 prime very well. Enough that they can get some reasonable bounds on this thing, which ultimately is actually how the production shows this thing. Okay, and you can do many other things with this as well. You can do, for instance, the K+3 version of my thing with Ben. Van der Kolk back in 1939 used a very, very similar technique to show that there are infinite many conversions in primes. It turns out that this problem is very similar to Van der Waals problem. This is Van der Waals problem. This is Van der Kolk's problem. So you try to put 3 guys, you try to have 3 primes given by 2 primes. In many ways, it's a very, very similar problem. The same technique works. So for the thing of Ben and myself, you can try running this whole type of machinery again. If you want to try to find a version in 4 or more complicated patterns, you find that it's not parallelograms now that control everything. It's parallel pipets. But you have to start dealing with how many shapes of this form you have in, say, the primes. And so you can go very long. All the Cauchy-Schwarz that goes on just fine. What gets stuck is that you want a nice formula for how many parallel pipets there are, and there's nothing like this. You try for analysis, again, this time it doesn't work. You get a formula that's just as messy as what you started with. It works. And the reason basically is that Fourier analysis is all about linear phases. And the reason why linear phases connected so with parallelograms is that parallelograms are connected to second derivatives, and linear phases are linear functions are precisely those functions to second derivative values. Parallel phases are related to third derivatives. And if you want to get a formula that captures the parallelepiped structure, you need to take into account every single phase whose third degree measures, in some sense. And those are the quadratic phases. And so, just dealing with linear phases is not enough. You have to start dealing with quadratic phases like this. And just even these are not quite enough as well. There are these sort of pseudo-quadratic things that happen as well. So a typical version that we takes the root 2x integer parts and root 3x. Turns out that this phase is also exhibits, it's not quite quadratic, but it's sufficiently quadratic that its third derivative vanishes about 1/8 of the time or something. You see, the integer part function is not quite linear, but it's almost linear. This is equal to this is half the time. And because of that, you can sort of half the time you're lucky, and you can sort of ignore the bracket or you can do the derivatives. And so this vanishes just enough to cause a headache. And so you actually have to check these things and deal with them. And so there's this whole area which is it's called quadratic Fourier analysis now to do all this. But it can be done, and it does. What it does give you is it gives you a way to. It doesn't quite give you a formula for how many parallelepipeds there are, but it tells you when there are too many parallelepipeds, when there are a lot of parallelepipeds, or when there are only as many as random predicts. And there's a very similar statement like this, that if you have that a set has the random number of parallelepipeds, it can only if it correlates, not with if it doesn't correlate with not the linear function, but this one is more common with quadratic functions. And then you can, if you want to deal with, say, the primes, you then have to start dealing with sums like this. But fortunately, this is still only one prime, and none of this know how to deal with expressions like this. And so you can estimate these correlations, and you can show eventually that apart from these obvious patterns of the like the involving bond and so forth, the primes do behave randomly in the sense that the number of parallelepipeds that they have is the right number. And because of that, you can actually start doing things like counting conclusion like 4, so on and so forth, and you can get formulas for how many persons before or less than that. Okay, so I'm out of time, but it's giving you an idea of how we use combinatorics when we use. It depends on how complex a pattern you look at. So if you want to find a question with 3, for instance, parallelograms are enough. If you want to find a question with 4, you need parallelepipeds. When 5, you need hyperparallelepipeds, and so forth.
Can you expand on the connection between Cauchy-Schwarz and the pigeonhole principle?
Okay. So suppose you have, suppose you have a set of pigeons. Okay, so the pigeonhole principle tells you that if you have more pigeons than holes, then there's just 2 pigeons exploring. The Cauchy-Schwarz inequality in this context says that no matter how many pigeons holes there are, you just count collisions total. The total number of pairs, possibly a diagonal, such that total number of collisions Squared for number of holes. You can conclude this, or what you do is that it's the same, you just work it out, it's the same sum of all holes. Of each hole, you count how many pigeons in that hole for UH. This guy is the same as UH squared. And Cauchy-Schwarz tells you this is bigger than UH. But the sum of the UH's, that's just the pigeons. Okay, so you get this formula. This is better than the Milliman principle because it implies it. So if P is bigger than H, then this is bigger than H. The H is the number of trivial collisions. P is equal to prime. No, not bigger than H. P is prime. So when P is equal to P prime, you get P collisions of 3, but when you have many more pitches in holes, you get many more collisions as well.
Good question. So this looks like a counterexample for compressive sampling and getting the regularity.
So the general principle that randomness is good. It just spreads things out so that it avoids lots of basically whenever you're in a situation where a lot of really unfavorable coincidences line up in a row could kill you, you could somehow make things random begin with these potential avoid all the bad coincidences. And so it's something in just a sense. Random matrix, and a lot of bad things that could have happened. So usually not happen.
So you gave a couple examples of cases where we have too many parallelograms. Presumably we can construct sets that have too few parallelograms.
No, this Cauchy-Schwarz argument, this theorem I had at the beginning, this argument that says that every dense set has some parallelogram. It tells you that every set has to have at least as many as this random number of parallelograms. So it's kind of
Potentially a stupid question, Department. I'm always amazed, knowing very little about number 3, the extent to which it has implications all over other parts of mathematics. Do any of these theorems have implications elsewhere?
Well, additive combinatorics as a whole has connections to other mathematics. The other two has my talks about that. These particular results, they do not specifically have applications. Well, actually, amusingly, this theorem of progressions of primes is this 10th problem, the undecidability of mathematical equations. The first proof of Hilbert's 10th problem, that it's undecidable, assumed that the prime is after mathematical equations. It was a conjecture at the time, and so in principle, this theorem would then have this mathematical properties. But then very shortly after, people discovered they don't actually need primes to complete mathematical equations. They only use simply almost primes in mathematical equations. Much easier to prove. That's one rare case with this application. But primarily, additive polynomial theory is I think, primarily driven by historical interest. The questions are very old. The oldest one that we can put up is a twin prime conjecture. The information present prime conjecture is 2 to 5. This may have been conjectured by the method. It's not written, but very close to guiding. So it's mostly for historical interest. I mean, it's only been 7,000 years. We can't just even answer these very simple questions about it. There's no